So take some notes on this and use this on the back side. When I look up here, I saw a whole lot of us take this factored form, rewrite it into standard form. Join the force for me. We're just going over numbers 1 and 2 really quickly, so grab a marker. So a lot of us doing this, okay? Now, mathematically, is this correct? Is this mathematically correct? Yeah, 100%. However, I gotta pause y'all, and I need y'all to remember this. What's the only form that you cannot solve a quadratic equation in? Standard form. So why are you going to go to standard form? If standard form is the only one that you can't solve a quadratic in, why are you going to go to standard form? I saw at least one person using the quadratic formula from here. But Davis, tell me this. If I tell you that A times B is equal to 0, what do you know? You don't know anything about A or B. What do you know? What equal? Well, yeah, I mean it equals 0, but like, what do you know about A or B? Okay, so we need to pay attention when I talk about these things, because, well, 2 times 3 equals 0. What about negative 4 times 5? What about negative 4 times 4? So what do you know about A and B? At least one of them's got to equal 0, right? Either A equals 0, B equals 0, or both equal 0. What is that called? Zero product property. So transitioning that over to here, when I have this factored form, what do we do with factors? Well, that's maybe what we eventually do, but when I say that word factor, what do factors do? They are multiplied, right? So we literally have a product of what? So guys, the whole point of factoring is so that I could use the zero product property. Either 3 equals 0, which it does not, or what else? Or 2x minus 7 equals 0. That's way easier than what a whole lot of us were making this. The whole point of factored form is that you can then use what key property? Zero product property. I need you to write that down if you did not do that here. Right? The whole point of factored form is to use our zero product property. The whole point of factored form is to be able to use that zero product property. Now, if it's not equal to 0, can you use the zero product property? No. Was it equal to 0? Use that zero product property, please. Yes, Lance.
So what do you do with that 3?
Is it great? The 3 equals 0? X minus 3? Oh, this 3 out here?
Yeah. Multiply and 4 equals 0.
Remember, I said it's a product of 0. So either 3 is equal to 0, which it's not, or x minus 3 is equal to 0, or 2x minus 7 is equal to 0.
So that 3 just goes away.
It just doesn't matter. It doesn't go away, but it doesn't matter. I am going to talk about one thing I saw. One thing I'm going to caution you is, I saw quite a few people distribute that 3 in and get 3x minus 9 and 6x minus 21. However, how many 3's are here? Only one. If I took 3 times 2 times 5, and am I going to rewrite that as 6 times 15? No, it's going to be 6 times 5 or 2 times 15. I only have one 3, so how many of these should that 3 be multiplied if I do that? only one of them. Which is why I always convert to standard form first in the industry, that 3, but we didn't have to do that at all, right? 3 does not equal 0, so that's obviously not a part of the zero product property. X minus 3 can equal 0. 2x minus 7 can equal 0, but be aware we don't distribute that 3 to both. It would only be to one of them, but we don't have to do that. What do I do here? By the way, I want to point this out. How many times do I see my variable in this equation? So what can I use when I only see my variable one time? What is it? Yeah, but how do we solve it? That's what I'm asking. There's two words / phrases I'm looking for. Say again, man. Well, I could simplify, but is there anything to simplify here? I could substitute, but guys, what's the solving process? It starts with an I word. Inverses. What inverse should I use? Right here. Addition plus what? 3. So just plus 3 there? Okay, so I've got inverses and what's that thing called? What I do to one side I have to do to the other? Properties of equality, right? So that created a 0. What I did to one side I have to do to the other. That's why you'll never hear me talk about moving stuff, because I'm not moving anything. I'm using an inverse to undo this, and to create an equivalent equation I have to do it to the other side as well. There's one of my solutions. Notice, and so for those of y'all who are wondering about that 3, and I'm going to come back to this other one in a second, but if I substitute this 3 in for x, okay, first off, what's 3 minus 3? 0. What's 2 times 3? Minus 7. I'm multiplying by a 0. So what's the result going to be? What's the product going to be? 0. That's the zero product property. At least one of my factors had to equal 0. That's it. So x is equal to 3 is one of my zeros. What do I do to this equation? Add 7, right? What's negative 7 plus 7? 0. So notice how to use that property of equality. 2x is equal to what? Now what? Well, 2x equals 7. Now what do I do then? Divide by 2. So I'm going to do that times 1/2. And so that creates a 1. Remember, we're either creating zeros or 1s for the most part. X is equal to 7/2. Here's my other 0. Guys, don't make your life harder than it has to be. The whole point of factored form is that you can then use a what? Zero product property. That's the point. That's why we care about that factored form. We don't ever want to get out of factored form. We want to go to factored form. I would make that note, right? Make your life easy. Don't get out of factored form. Go to factored form. What are your questions about this first one here? About A? Going once. Going twice. So, second one. Hey, what form do we have here? Vertex form. And again, only standard form can I not solve right away. Vertex form I can solve right away. How? Inverses with properties of equality. Notice how many times do I see my variable? Once. So I'm going to use inverses with properties of equality. That's it. Now, what's the first inverse I need to use? That's an important step. And again, let me remind you, this is not the only inverse I could use, but it's the way I recommend because it's the most straightforward. Addition? Adding by 4? Added by 8? Okay. Remember, 8 is the last operation being done. It's x minus 4 because of the parentheses. X minus 4 squared. 2 times x minus 4 squared, right? Because multiplication happens before addition and subtraction. So I add 8. That's the easiest thing to undo right away. Property of equality. Now what do I do? multiply by that reciprocal, divide by 2, whatever makes your heart happy on that one. Again, I just recommend the reciprocal, because what's half of 2? 1, right? So what does x minus 4 squared equal? 4. Now this is the only really tricky part. You've been using inverses with properties equality for years. What's the tricky part at this point? What about that exponent? What do I got to do? Yeah, but how do I get rid of it? There we go, right? And instead of just saying get rid of it, inverse it, right? Like the inverse of a square is a square root. Okay, cool. But here's the tricky part, right? That cancels out the square. It actually makes it an exponent of, does anyone know what it makes the exponent? It makes the exponent of 1. Right? Notice again, we're making zeros and ones. So what does x minus 4 equal? Sure.
2 and negative 2.
2 and what?
Negative 2.
2 and negative 2. We've got to remember the whole idea is what squared equals 4. 2 squared equals 4, right? But what else squared equals 4? Right. So I need a positive and a negative 2. You can split into 2 equations if you want. I'm going to write it actually just like this. Because when I add 4 now, 0. I got x equals 4 plus or minus 2. What's 4 plus 2? What's 4 minus 2? Oops, positive 2. These curly brackets are just a set notation. You don't have to do that. But that you'll see some textbooks use that. You'll see some teachers use that. So I just want to show that. Those curly brackets just mean a set. And I have a set of 2 numbers, 6 and 2. Those curly brackets just mean a set. I was freaked out by it the first time I saw it. It's the easiest thing though. It's a set. Okay. So don't forget, the goal is to go to factored form so that we can use the zero products property. The goal can be to go to vertex form, because what can I do from vertex form? You can use inverses with properties of equality, right? So think through those things. Mr. Javi last week worked through a task with y'all where you got to look at and analyze the equations to figure out which one's the most efficient method to use. So I'm now going to give you about 15 minutes to continue working on the back side. One word of caution I'm going to point out to you is how many of those equations do you have to solve? Just 2 of them. However, if you have extra time and you want to go for a third and show me 3 different methods, then that's going to that exceeds level. Remember, for the proficiency scale, the target is that you can regularly use 2 different methods. Okay? Does anyone need me to leave this up here before I erase it so you can make some notes to yourself? Okay, just really quickly. I'm not leaving it the whole time. Oh, you didn't write any of that down for that one. I'm going to take a picture of it and I'll share. Do what? Well, did you show me evidence of understanding? But I did that.
I just get time to work.
That's for your notes to your future forgetful self. Okay? Yeah. Well, the whole goal is that you can now apply that to those equations on the backside. Okay? That's why I let you take those notes as we went over this. So. You had to use them. Beware, they will not be up there. All right, we're going to talk through strategy with these 3 equations. I'm going to talk about recommended strategy. Well, first things I do want to recommend, some of us need to do the check your understanding more. Quick show of hands, how many of us have worked significantly on the 5 sets of check your understanding that I gave for solving quadratic equations? 1, 2, 3. So, if we have not worked on those, remember, I don't give you mandatory homework that I'm going to check because it's going to show up on assessments. you need to work on those check the check understandings. It's not to say that's going to make it immediately easier, but the fact that we're struggling in class and the fact that we're struggling to demonstrate understanding is very indicative of we're not doing those check your understandings. So let's talk strategy-wise first. Strategy-wise, which of these equations can I not factor? D, E, or F? D, cannot factor it. There are no factors of A times C that add up to B. Are any of the other ones not factorable? Both. F is not factorable either. If you're going to factor, this is the only factorable equation. Now there's something we have to do before we can do that, but I would be aware and make that note. That's the only factorable equation in there. The only one. We're going to talk about y in a second. So I'm going to make a recommendation. You don't have to follow this one. Does anyone know which of these I would recommend using the vertex form with? D. 100% D. I would recommend vertex form here. I can't factor it. Could I use the quadratic formula on D? Guys, remember which quadratic equations can we use the quadratic formula? All of them in standard form as long as what is true is equal to what? 0. So which of these as it currently stands can I not use the quadratic formula on? E, right? Keep that in mind that to use that quadratic formula, it has to be standard form, it has to equal 0. But yeah, that I would recommend vertex form. So let's talk about the vertex form. And let's point this out. This is the only one I would actually use vertex form. Because if I'm going to use vertex form, like I'm going to convert it to vertex form, what do I need to calculate first? What's like that starting point for vertex, huh? H. And how do we calculate H? Notice that would give me a positive 4 divided by 2 times 1 or 2. That's a nice number. Is that a nice number? No. Can I still do it? But it's not a nice number. F. Nice number? Can I still do it? I mean, I think you even did the vertex form on F there, right? It worked out. It does. Vertex form does always work. It's just not always easy. And so we'll look at F. F is one of those that I will say this, I'm very partial to the vertex form. I just love it. I'm a nerd. I get it. But more than likely I would recommend quadratic formula there. So let's start with D. And so update your knowledge on these things, okay? I didn't plan on going over this right now, but looking at some of the struggle we're having, I felt like it would be most appropriate to go ahead and go over this and make sure we're understanding, okay? Once again, I can't factor this one. I saw a few of us trying to, but if I were to factor, what's the starting point of factoring? I just want to point this out. Again, we're not going to, but what would be my first step in factoring? That's the second step. I mean, I guess I can technically start with the box, right? So don't write this down unless you want to make a note about why not to do this. But what do we know inside this area model? So I know this is what? X squared. What else do I know? The bottom right is 2. And I still need this. And so Landon, you started to refer to the A times C. And Bella, this is what you ran into. You started trying to look at this and you're like, I can't find any factors of 2 that add up to -4. Can you? Well, if there's no factors of A times C that add up to B, you know what I can't do? I can't factor it. I cannot factor it if there's no factors of A times C that add up to B. So if you need to make that note to yourself, please make that note to yourself under D. There are no factors of A times C that add up to B. But vertex form, man, that's a nice pretty number. It's an integer. It's going to make my life easy. What do I still need for this vertex form though? I still need K. And, well, I have A. A is 1, right? So I already have the 1. I don't really need that there. X and what? Minus 2 squared. How do I get that K though? Remember, H is my input and K is my output, right? So F of 2. And so if I type that into a calculator or do it by hand, whichever makes your heart happy, you get negative 2, I think. Yeah, negative 2. And this is what we talked about earlier, so I'm not going to go through it slowly, but this is now vertex form. And from, well, up to this point, what questions do you have? Is that, we good with that? Converting it? Okay. Once I have vertex form, I'm going to use my inverses. Plus 2. Now, remember, when we're using inverses of those properties of equality, what's our goal? What are we trying to create? What kind of numbers? Zeros or? I already have a 1, so I don't need that there. So I just want to point that out. You can put the 1, you just don't have to. Square root, that's supposed to be a 2. And, bless you. And I'm going to make a recommendation here. I'm going to leave it right just like that. Square root of 2. I don't need a decimal. Decimal's not going to help me. If I was trying to graph it, maybe I get a decimal there. But the square root of 2 is an irrational number. What does that mean about our decimal? Yeah, is there going to be a pattern to those numbers after the dot though? If it's irrational, that, so like, notice, so let me show you this, 7/3, that's 2.3 repeating. 6 divided, that's not a good one. 6 divided by 4, that's 1.5. So, oh, we haven't talked about rational numbers at all in this class, have we? Okay, so this is going to help you with the lesson we're about to go into, so go ahead and pay attention to this. Rational. What's the beginning of that word? Ratio. I don't know if a teacher's ever talked about this before, but a rational number can be written as a ratio of integers. That's why we call it rational. Okay? So we call it rational because it can be written as a ratio of integers. And so if we can write it as a ratio of integers, either the decimal is going to repeat or the decimal is going to terminate. So if that decimal repeats or that decimal terminates, that's a rational number. So what does that mean if it's irrational? That does not repeat, it does not terminate. Okay? Which means the square root of 2 here, that decimal is going to go forever without terminating, without repeating. So I can't write all that out. So if I write out a decimal, it's an estimate. But if I leave it as square root of 2, that's as precise as it gets. Okay? By the way, do note for an irrational number, does anyone know what the prefix ir means? It literally means not. So, rational and not rational. That's all that is. That's where those words are coming from. Mathematics is not random, we are intentional with our language of things, and so those those names are not made up. So what do I do from here to solve for x? Plus 2. And so we usually put our integer first, and so I would literally just leave it as 2 plus or minus the square root of 2. That's why I would leave it as that radical. Okay? So you can just leave it as 2 plus or minus the square root of 2. By the way, you remember how we talked about the fact we can't factor it? The fact that we can't factor it? Ooh, I'm going to hold off on that detail. I'm going to talk about it with you. Actually, I'm going to talk about it after that. Sorry for lying. Okay? E. What do we decide we're going to do? Factor it, right? But if we're going to when we talked about this earlier, so actually as of right now I cannot factor it, but if I want to factor, if I want to use the quadratic formula, what does that equation have to equal? Zero, right? Now I'll point this out. Did I say that you have to equal 0 for the vertex form? And you don't actually, okay? But if everything else needs to equal 0, what's a safe step to just go ahead and make your life easy? Always make it equal to 0, right? I think that's a great place to start. All right, what's 3 minus 3? Okay. Notice now, and so Landon, you talked about using that area model from the beginning. Personally, even before I start to write out my area model, I'm going to check to see, are there factors of A times C that add up to B? So before I go through the effort of writing out the area model, 2 times -4, what does that equal? -8. Are there factors of -8 that add up to -7? Ooh, be careful, -8 and 1. Right? Because if you do -1 and 8, that's a positive 7. Right? If you add those together. All right, now I'm jumping to my area model. So I've got my 2x squared, got my -8x, plus 1x, and minus 4. Does it matter what order you put the linear terms in? No. If you put in the different order, that's totally fine. Okay. Do note, why do I call these linear terms? It's almost like mx, right? 1x, 8x, that's x to the first. What would I call this term, by the way? Just to make it easier to talk about these things.
Quadratic.
Is it exponential or is it quadratic? It's a quadratic equation, isn't it? If it's x squared is quadratic, what do we see if it's exponential? The exponent is a variable in x, right? Remember, exponential has that variable x. I call this a quadratic term. So quadratic, linear. Anyone remember what we call it when it's doesn't have a variable with it? Constant. Right? So you can talk about them that way. Quadratic, linear, and constant terms. Okay, 2x squared and 1x, what do they have in common? Just an x, okay. What do 2x squared and -8x have in common? They both have a 2 and an x, right? Notice 2x times x is 2x squared, right? What do -8x and -4 have in common? They're both negative and they have a 4. And just take a second to check yourself, right? 2x times -4 is that -8x. And so what needs to go here? What is it? A 1. And a positive 1. That makes it all work. Now that I got a factored form equal to 0, what can I use that we talked about earlier? Zero product property, right? The factored form is your best friend for that zero product property. And then I only have the variable one time in each equation, and use those inverses. X equals 4. X equals -1/2. And Miles, I heard you say, at least I got the right answer, right? I need to use the quadratic formula with it, right? Remember, can you always use the quadratic formula? As long as that standard form equals 0. And how many methods do you have to know how to do for target on the proficiency scale? Just 2, right? So if you want to dive in deep and go quadratic formula and go vertex form, you can do that. Factoring, when you get comfortable with it, actually is significantly faster. And there are going to be some pre-cal teachers, some calculus teachers that expect you to always to be able to factor, but I'm not one of those. If you can do it at least one of the ways, we're good to go. Okay. Then we recommended quadratic formula. Now again, Demia, you did this vertex form. It totally works. I'm going to talk about a couple of small details when Demia did this vertex form. But yeah, I would use quadratic formula. It's actually not too bad as long as you use your calculator. And there's something that I showed Demia that actually makes the vertex form pretty doable on this one. But I will point this out. This is why you want to be strategic with the methods that you choose, because some methods are easier than others at certain points. So opposite of b plus or minus square root of b squared minus 4 times a times c, all divided by 2 times a. Okay. What was 9 minus 4 times negative 2 times 4? 16. Was it 41?
Yeah.
Divided by negative 4. And so at this point, the only thing that you could either leave it like that, because notice what kind of number is this going to be? That's going to be irrational, so you can totally leave it like that. The only thing is, and some math teachers are going to be this way, we don't like negatives in the denominator, so I might just multiply the top by negative and the bottom by negative, because it's the same as 1. It doesn't change the identity, but it makes things a little bit easier. And because it's plus or minus, guess what? It stays plus or minus. You'll see some people actually switch it to minus plus. That's silly. You don't need to. That's how I would have finished. Okay. Quadratic formula, it works. Sometimes it's a little bit more complicated, but let's see. H came out to be 3/4. K, I believe, comes out to be negative 41 divided by 16. So be careful if you did not get that, Demia, because I don't think you did. But if you substitute that 3/4 into that equation, use the calculator, it'll kick out negative 41 divided by 16. And, oh, wait, is it 16 or 8? Sure about that? I don't doubt you, but I doubt you, sorry. It is okay if you leave it as decimal, but show me the steps of simplifying. And again, just make your life easy and just leave it as a radical. Because again, it's irrational. Technically, those decimals didn't end there. So let's see, negative 2. I'll let you see it as I type it in on here. So negative 2. Hold on. Negative 2 times 3/4 squared, was it plus 3 times 3/4 plus 4. Yep, way to lie to me. Positive 41 divided by 8. Positive 41 divided by 8. Alright. I'm going to use my inverses. And again, I'm just going to show you one quick detail here to connect it to that vertex or that quadratic formula. Remember, this is actually the clear reason why I like to use the reciprocal here. Because if I divide, I'm going to get this divided by negative 2. That's really ugly. And that may have been what you were trying to do, Miles, that made it really ugly, but what if I just use the reciprocal? A negative times a negative is a positive. And what's 41 times 1? It's 41. And what's 8 times 2? So that's why I use the reciprocal, is because when I'm dealing with fractions, it's really easy to multiply fractions. It sucks to do division. Now from here, the last step I'm going to show you is this. Take a square root. When you take the square root of 41 divided by 16, this is actually going to tie into what we're about to do pretty heavily. When I have that, there's a property of radicals. I think I might have mentioned this yesterday. But there's a property of radicals because it connects to exponents where you can actually just split it up as the square root of 41 divided by the square root of 16. Right? And what's the square root of 16? 4. So positive, negative, square root of 41 divided by 4. And so when I add 3/4 to both sides, what do I get? 3 plus or minus the square root of 41, all divided by 4. Same exact answer. Solution. Okay, so update your knowledge. Why do you have a pencil in your hand? You're supposed to be updating your knowledge. Alright, so that's that. Please put, the last thing I want to point out is this. The two methods that came out with irrational roots or solutions, we could not factor them, could we? The one that had rational zeros, what could we do? What method could we use? Factoring. What does that tell you about the factoring process? What's the only type of zeros you can get while factoring? Rational, like 100%. That's the reason why you can only sometimes factor, is because when I factor it like this, notice how I have integers in here, so I'm going to get rational numbers out of those integers. So I want you to keep that in mind, that the only time I can factor is when I'm going to get rational roots. Okay? Questions, comments, concerns? Demonstrate your understandings together. You should have updated your knowledge, so I'm only going to score these. I am not going to provide feedback, but put them together. I'll come collect them in a second. And we get to move forward with this. We're going to continue applying these things. I will make a note of that. So if you were struggling with this, that's okay. We're going to continue to apply these ideas. By the way, do you know how you could have checked your answers for all of these? There's two major methods. So you could have substituted your answers in for x, and what should it tell you? 0, or if you typed in the equation, it should tell you true, right? That's a good question. Do you want me to answer this question first before? Okay. So let's say that you had 2x squared minus 4x plus 2 equals 0. If I were you, and your previous teachers probably talked about this, I haven't yet, I should have. Before I try to factor, before I try to do anything, what do you notice about all of those terms? They can all be divided by 2. And so, I wouldn't necessarily divide everything by 2, but what I would do is I would definitely factor that 2 out. And then I would just work with this. Does that make sense? Because that would allow me to think about that zero product property, things like that. Now, that only actually matters if you're going to try to factor. If you're not going to try to factor, it doesn't matter. It's still useful, right, to factor out your greatest common factor, but notice how it's a greatest common factor, so it matters the most with factoring. Okay, so good question. If there is a common factor in all terms, yeah, go ahead and take it out. It makes your life easier. All right. So we should be able to substitute those values in, and they should make the equation what again? True. So let me do this really quickly. So I'm going to take 3/4 plus the square root of 41 divided by 4. I'm going to get a decimal version of that, okay? And I'm going to do minus. Alright, so notice how we got 2 decimals. The reason why I'm going to show this to you is this is actually going to be very useful to you to check yourself moving forward and for the next unit about imaginary numbers. What have we been trying to calculate or identify this whole time? Anyone remember the name of, like, why we needed this unit on solving quadratics? What are we trying to find? What feature? Say again? Zeros. Woo, thank you. Which are also called roots, which are also called x-intercepts. So remember, the context of it matters. X-intercepts if it's on a graph, zeros of the function, roots of the expression. It's a whole complicated mess. But what was equation F? Negative 2x squared plus 3x plus 4? So I want you to notice What were those decimals I got again? Negative 0.8 something? What does that look pretty darn close to? Negative 0.8 something. The other one was positive 2.35. Does that other root look like it's about 2.35? Now it'd be really cool if the calculator could actually tell me what those are, right? What's the button lets me do cool crap again? Okay, let's go to menu. Anyone see anything here that might be useful in maybe finding those x-intercepts? What is it? Oh yeah, let's try to analyze this graph. Anyone see anything useful under analyze that graph? Ah, this is why we need to know terminology, right? Those x-intercepts are also called zeros. So if I check myself, so 0, lower bound. Remember, this is like, I don't know that we did this much. I don't think we used the lower bounds. Did we use it for the area under the curve for z-scores, actually? No, because we just did, never mind. I'm thinking of something different. All right, lower bound, that just means to the left. We did lower bound and upper bound with normal distributions, right? But we didn't do it like this. But lower bound just means to the left. So I hit enter. Now it asks for an upper bound, so I go to the right and I hit. Does that number look familiar? Heck yeah. All right. Let's check our other one. Does that number look familiar? So here's one thing I want to point out, and I need you to be aware of this. Can you check your solutions this way? Could you note that on a test or a demonstrated understanding? Say, hey, Mr. Kinney, I checked my answers by graphing, and I found the same roots. Is that evidence of understanding? 100%. On top of that, when I think about looking at, actually I'm going to hold off on this, but we need to notice our roots, right? We got 2.35 and negative 0.85, those zeros there. So check yourself. Just take an extra second. Oh, that's what I was going to say. Let's say you get your answer wrong. Like you've done this whole work to do vertex form, you got to the end, you got solution. Just you working it out using vertex form, is that evidence of understanding? I mean, that's not necessarily that it's right, but if you know how to use vertex form and you show the steps to use vertex form and you get to the end and you have x equals, is that evidence of understanding something? 100%. But is it easy to make a mistake at times? 100%. So if you were to take the time to go into the calculator, find your zeros, and say, hey, Mr. Kinney, I did the work, you can see that I understand something, but I got my roots wrong. Do you think you checking yourself and noting that these are different from what you got is more or less evidence of understanding? It's more evidence. And so I want you to think about that, right? Like, take the time to check yourself. Take the time to use that graphing calculator. And heck, if you're just completely lost, what could you use as long as it's a calculator portion of the test? Calculator, right? Okay. So keep that in mind, that we can find our roots that way. And that is impactful for what we're about to do. All right, so we can always improve our understanding, update your knowledge from where we've been. Right? We, at this point, hopefully, by the way, notice, what is this last one right here? Determine what type of zeros a quadratic equation has by examining the function's graphical representation, right? So, we just saw that graph. Those roots were rational or irrational? They're irrational, right? Those decimals that didn't really terminate or repeat, those were irrational roots. If we had nice rational roots, by looking at the graph, you could say, hey, it's going to be rational roots, things like that. We're going to go into more detail with that soon, though. But those are the things we need to be able to do. Again, zero product property. Take advantage of that. I want to get into imaginary numbers at least a little bit today. So I'm going to hold off on this spicy a little bit. It's going to be a good problem to start on tomorrow. I know we looked at it barely yesterday, but we'll look at it to start tomorrow. We'll talk through all that, All right, so this is the second proficiency scale. It's on the back side of the one you already had. Okay, so the second proficiency scale, if you want to look at it. Notice the foundations here. I'm going to go ahead and tell you. The foundations here are things that we should technically be able to do at this point. However, I understand if we can't. We're going to talk about some of these things more today. And the reason why I say we should be able to is these are things from Algebra 1. But again, I understand that we can't. What are some of the things that we do already know? The terms or the concepts? Radical and radicand. What's the radical? Square roots? You don't have that one? Okay. What other, so which part, thank you. I should clarify this. So David said square root, right? Did you know that the square root is not, the square root has more than just the radical? Yeah, here you go. Set it right here for a second. So like when I look at a square root of 41, which part of that is the radical? So, which part of that is the radical? Can someone come up here and just circle the radical piece? All right, so square root of 41, cube root of 41, all that fun stuff. Can I get someone to come just circle the radical part of this? Any guesses, predictions? The 3. Just a guess. So that 3. By the way, it's not written, but did you know what's right here for a square root?
Oh, 1.
It's understood too. Remember, it's the inverse of a square, right? Okay? 4th root. 41. So these indicating the roots, that's actually called the index. The index indicates which root it is. Index indicates what root it is. So which part's the radical? No, yeah, the 3, the square root, the 4. Wait, but actually we already know what that 41 is. It's called it's the symbol. Guys, the symbol is the radical. Yeah. That symbol there is the radical. Okay? The index indicates what root it is. What do we call this 41 in each of these? The radicand, right? Okay, so be aware of that. The index tells us what root we're dealing with. The radical is just that symbol. And then whatever's inside of the radical is called a radicand. Okay. What other terms do we hopefully know?
Irrational and irrational.
Rational and irrational. We already talked about that. Any of these other ones, hopefully? Integers. What are integers?
Like,
Someone give me an integer. 3. There's an integer. Give me another integer. 2. Give me another integer. 9. Give me another integer. Okay, so what have we said so far? 3, 9, 2, 15. Okay. Those are integers, but those are also a special type of integer called the whole numbers. You're missing a whole bunch of numbers that are inside of the integers. So we use a W, by the way, for whole numbers. We use a Z for integers. It comes from the German word for number, Zahlen maybe? I'd have to go back and study it. I was just confused one day why in the world we use Z, and I found out. Anyways, so what are we missing that also is an integer? So decimals would not be integers. Remember we talked about the rational numbers are the ratio of integers, and those decimals terminate or repeat. Say again. Say it again.
Negative.
Negatives. So 3 or negative 3, 9 or negative 9, 15 or 2 or. So these are all whole numbers up here. Those are only the whole. The integers would be the positives and the negatives. Okay? Hopefully that sounds familiar. Yeah? Now, I do have whole and natural up there. Does anyone know what the difference between whole and natural is? They're also called counting numbers. Where do you naturally start counting? 1 and 2 and 3. So those are natural numbers. So the whole numbers also have the number 0. So natural numbers are 1, 2, 3, 4, etc. The whole numbers start at 0. The integers are the positive and their opposite. So the whole numbers and their opposites. No decimals with whole numbers. Okay? And then you mentioned real numbers, right? But what are real in comparison against? What's a real number? But what is it? We were able to establish what a whole number is, an integer, a natural number, but what's a real number? So we don't fully know yet. You've heard of it, huh? See, not all numbers are real numbers. Not all numbers. Okay, so we need to explore this. So we're going to get into more of real numbers with this unit here. There we go. But hopefully we can do some of this. We're going to talk about simplifying square roots together soon as well. But what are we adding in under the target? Complex numbers and imaginary numbers. By the way, anyone want to take a guess at what the opposite, I would say, of a real number is? I want you to think about this vocabulary here, these concepts. What is going to be opposing real numbers? Imaginary numbers. Oh, these things are real or they are imaginary. Okay, so here's what we're going to start with. We're actually going to jump. No, we're not. We're going to start with topic 1 of this. And so I am skipping the very first page, but I want us to just talk about Elena and Mark here. Right? So Elena, x squared plus 1 is equal to 0. X squared is equal to negative 1. And so Elena says x is equal to a positive or negative 1. Elena says positive or negative square root of negative 1. Whereas Mark says it's positive or negative 1. Who's right? Elena. Why? What did Mark do wrong? Anyone know? So by the way, these are pages you already tore out, but actually you only hit the lights running, Miles. Ooh, that was a struggle bus. Alright, so what did Mark do wrong?
He didn't keep the square root.
Well, I mean, it looks almost like he's saying that the square root of negative 1 is 1. So let me ask you all that. Is the square root of negative 1 1? Why not? I will point this out. If I were to say the square root of 4, what is the square root of 4? 2, and that's because, what is 2 squared?
It's a non-real calculation. You can't square root it.
Oh yeah, you can. We're about to learn how to do that.
I would say non-real calculation.
Well, what would non-real be?
Not true. Not true.
Imaginary?
Say it again.
Imaginary.
Oh, non-real might be imaginary.
Like you said.
Okay, right here though. Listen, square, but I want you to go beyond the calculator. I want us to understand this. The square root of 4 is what? 2. Why? Because 2 squared is 4. So if I were to ask you 1 squared, is 1 squared going to equal negative 1? No. Right? That's not going to work. So that's why Mark did it wrong. Also, it says right here, hey, look at the graph. If Mark is saying positive or negative 1, those should be the what for this graph? The roots? What's another way to say that, looking at that graph? The zeros or the... Hey guys, do we have a positive and negative 1 x-intercept?
No.
Oh, no. In fact, if I look at that graph, what x-intercepts do I have? None of them. Oh, crap. Yeah, we don't have any x-intercepts, but we've talked about this before. Every quadratic has how many roots? 2 roots. Every quadratic has 2 roots. Anyone remember the term for that? It's pretty fundamental to algebra. It's also on a proficiency scale. It's pretty fundamental to algebra. It's on that proficiency scale. It's pretty fundamental to algebra. What is it? Say again. It's 3 words, and it's pretty fundamental to algebra.
The number I.
What? Say it again. No. Guys, I'm not trying to trick you. Listen to the language I'm using. It is fundamental to algebra.
Fundamental.
Oh, is that what you were saying? Oh, I didn't hear. Fundamental theorem of.
That's 4 words. Algebra.
Oh, I'm so sorry. I ignored the word of. All right, fundamental theorem. I can't count. I'm sorry, guys. It's fundamental to algebra. A quadratic is going to have how many roots? 2. A cubic is going to have how many roots?
3.
X cubed is going to have 3. X to the 4th. A quartic is going to have 4. Right? The degree tells us the number of roots. So, frick, we got to find out how many roots this has. And we're going to talk about this tomorrow more heavily, but I just want to point this out. In order to calculate the square root of any real number, there must be some way to calculate, or the square of any real number. Guys, we got 2 minutes. Hold on 1 second. We have to be able to calculate the square root of a negative. What they're saying here is if I want a number squared to equal 4, I got to have a square root of 4. I have that. But the question then becomes, well, what squared is negative 4? And for the longest time, mathematicians did not think it existed, so they said it was what? Imaginary. But these imaginary numbers are very real. If you like technology, everything with electricity runs off of, anyone guess? Imaginary numbers. It's not that they're actually imaginary. They exist, we just didn't think they did originally. They're actual numbers. Well, once the name's stuck, it's stuck, okay? But, last thing, really quickly. So if I squared, so we established this imaginary number. Notice what do we use for imaginary? I. If I squared is equal to negative 1, what would I equal? Say again. Not 1. So think about this. Right? The square root of 4 is equal to 2 because 2 squared is 4, right? So what is just the I going to equal?
Negative 1?
Square root of? Negative 1.
Yeah.
There is the number I. I is the square root of negative 1. We're going to talk about that more next week. Or tomorrow, not next week. I'm here. I'm present.
Oh.
Yeah, it's okay. I have one cracked and I have a couple missing.